Hello, welcome to CSE 351 Introduction to Data Science. Today's topic is about basics of probability and statistics. So, for the sake of compactness, I just use the term of stat or statistics, which all both refer to statistics and probability. Later on, we will show that they are very connected, and so I just use the term of statistics. So the first question you may ask, why do I need to know about statistics for data science? So statistics is one of the pillars of data science, without which basically we are not able to do any analysis. So we are using statistics for two different mainstreams in data science. The first one, basically, if we have a population, we wanted to infer some information about this population, some statistics. For instance, it may happen to all of you, you received a grade for a course, but you don't have any information about other students' grade. So let's say if your grade is 30 out of 100, you might be very worried. However, until you don't have any idea of the entire population, you cannot say I did bad or well or average in class. So what you do, you usually send out an email to instructor and ask him or her to provide some statistics about the grades population, and then the instructor will post the average and also the standard deviation, median, mean, max of this population. Then you will gain a much better insight about where you are standing in class. For instance, if your grade is 30 and the average is 10, then probably you're going to get an A in this course, even though the grade is out of 100. So another reason is we are dealing with many phenomena in this world and also in different fields of science, technology, engineering, that basically their nature is uncertain. Because their nature is uncertain, we cannot have a deterministic view toward them. Therefore, we need to provide, quantify them in the sense of some uncertainty. One very popular example is weather forecast. So when you're checking a weather forecast website, probably you are not looking for something certain. You are always looking for some chance of participation of rain or snow. So for these two main reasons, we need and also we use the statistic in data science. So we are given, tens of terabytes of data, and then we are seeking and looking for some information and insight in this data. However, nothing is certain. So we need to provide some statistic and also quantify the uncertainty about this data, right? Another example I can tell you, let's say we are doing some sort of handwriting recognition. Probably if you are having a handwriting of different people, even human beings sometimes make some mistakes, right? And then we should have some probability that if you're saying this letter is A or this word is cat, what is the probability that this word is cat? So whenever we do prediction, these predictions are not 100% certain. There is some uncertainty about these predictions. Therefore, we also use statistics to show that uncertainty. So these are two main reasons why we are using statistic in data science. Let's consider an example through which I show you different definitions and concepts rather than just going through some definition right away. Let's say you are hired as a data scientist in a firm, and this firm is not Facebook or Instagram. And then this firm wanted to get some info about Stony Brook University students, and you wanted to find out the average number of times Stony Brook University students check their Instagrams, and also the average number of times that our students, they check their Facebook. So this is a project given to you, and then you're bought a ticket, you're flying out to Stony Brook, and you have 2 days to complete this project, and also you don't have access to any database. So how would you conduct these experiments? I also have in mind we have 32,000 students in Stony Brook. So we call the average or mean of number of times a student check their Instagram as M1, and the average number of times they check their Facebook as M2. So instead of using this informal math language, we use M1 and M2 to denote to this average. So I want you all think for a minute or so to see how you're approaching this problem. Okay, so how to solve this problem and how to report the result to your manager. You have only 2 days, and probably if you want to go and ask all Stony Brook University students about these numbers, you're going to run out of time. So what you do, you are saying, okay, I'm going to run a survey, and then probably set up a booth or walk all around universities and ask students a questionnaire. Okay, could you please tell me how many times you're checking your Instagram? Even though they don't have a very clear picture, but they can tell you, okay, within 1 minute or 2 minutes or 1 hour or half an hour, I usually check my Facebook and Instagram 5 times, 10 times. And then you're writing down, and then also you, for the sake of privacy, you don't record a student's name or ID. So what we basically do, we are having a large population, which is the entire Stony Brook University students. And then because we cannot reach out to all students, we go and select some samples from this population. And then from that population, we record their numbers. So it's a sample space, right? And the red one is the entire population. So this one is basically entire population. Okay. So also suppose that within 2 days you manage to stop around 1,245 students, and then you record a number of times they have checked their Instagram or Facebook, and then you manage to compute the mean for both of them. So we all know how we compute the mean. So basically, the mean is taking the average. We sum up number of times the first student check, number of times the second students, number of times the last students, 100 to 55, and then divide all these numbers by 1245. This gives us a very easy way to compute the sample mean, right? And then we do the same for M2. We have M1 and M2. There's a reason I brought up two means, because later on we are going to introduce these statistics in domain of vectors and also matrices. So because we are working with high dimensional data in data science. So for now, let's assume that our space has a dimension of 2, or the first dimension is Facebook, the second dimension is Instagram. Okay, well done. Good job. You managed to provide the mean of M1 and M2, and then you fly back to your company, and then you report this result to your manager. Unfortunately, manager get back to you and say, okay, the numbers you have provided, M1 and M2, are not consistent with the results obtained from 3 other data scientists who contacted these experiments like 2 months ago and 3 months ago. Then this is a real problem, right? So how we are going to, or how you're going to convince your supervisor or manager your results are more consistent and true. So in here, we need to establish some foundations, some definitions, and then some concepts that all of us are agree upon, and some measure to quantify the statistics we obtain, and then in order to be able to compare, and then to see if our results are consistent and significant compared to others, and how to fix it if our results are wrong. So to answer all these questions, we need to know statistics and also statistical analysis and parameters in order to provide a reliable measurements from an uncertainty such that other people can read and understand and agree upon, and also take action from these numbers. So I leave it to you for now. Why do you think the results you have obtained are different from the three other colleagues? So I will just bring up some issues, and then later on we'll see how we're going to fix them. Let's say again we have this cloud shows the entire Stony Brook University students space, and then as I said, you're taking samples. You have collected 1,245 students. So that day, because the weather was hot, and then you don't want to walk across the campus, you only stayed in food court and then two other departments. So let's say you only stayed in here and in here. So let's say you only stayed in department of athletic center and also close to a gym. And then you got all of your samples from these two subspace of the entire population. Your results is somehow different from others because the way you are sampling this population is kind of biased because you didn't sample the entire population uniformly. So you didn't walk through other departments and check from them. So ideally, the way you need to sample is to go from, you should uniformly samples from all populations and then take the average. So we see that one way to have a better and consistent statistics about the population is the samples we are retrieving from that population should be uniform. Otherwise, the results are biased towards one attribute. I can give you another example. Let's say you are asked to obtain the average height of students at Stony Brook University. You are only sampling from a place at a certain time after a basketball game. So what will happen is the average height of students Stony Brook goes up because you're sampling in biased, right? So how do you address all these and how to have a definition for all this? Here we introduce some definition. First one is population. Population in statistics is the collection of all subjects or object of interest, and also it is not necessarily people. In our example, it's all Stony Brook University students are our population. Let's say you wanted to obtain a measurement from some breast cancer genomic information. So what is the entire population? The population is, let's say if you focus only on United States, it's all patients who are suffering from breast cancer all across US. So that's the entire population, you see, even though for some patients we don't have any sample, right? Sample is a subset of population used to make inference. By inference in here, we mean that we can compute some statistics about the characteristics of this population. So these characteristics basically reflect some uncertainty about this population. So in simple words, these statistics are average, mean, median, mode, and some other statistical measurements which will be explained later. Population parameters. So these are some numerical characteristics of a population, and this is fixed and unknown. For instance, for our case, if you go and ask the entire Stony Brook University students from each individual about number of times they check their Facebook or Instagram, and then if you compute the average, this is called the population parameters. This is the mean of this population. It is fixed. It's not going to change because you consider the entire population. Unfortunately, the population parameters are usually unknown because we don't have access to entire samples, right? So let's say you wanted to see what is the average weight of an elephant. So you can go and find samples, take samples from different continents, different countries, but you wouldn't be able to collect and reach to all elephants in this world. So basically we don't have the average. What we have is we have sample statistics. So sample statistics are those numerical characteristics of the sample data taken from the entire population. So sample statistic basically provide an estimate of the population parameters, and it's very extremely important to understand this concept. So when we say we collected samples from a population, when we compute the mean, that's basically is an estimate of true mean, an estimate of the true mean. So this is basically how we do. For ideally, we are interested in order to find the parameters of a population. But because we don't have, we basically compute. So we have the sample, this is population. We sample from this population, we get a subpopulation or a sample which hopefully truly represent the entire population. We compute the statistics. So this statistic could be mean, variance, or other statistical measurements, and then these statistics will provide some info about the parameters of this population. So this is another example. We have this entire population in here. There, as I said, these are people, but there could be also non-human beings, some other things. We would like to find the mean of this population, but because we don't have access to entire population, we sample a subpopulation, which call it samples, and we compute the mean, which is, we call it the statistics of these samples, and then that will provide some info about the true mean. So basically what we wanted to do, we wanted to compute the population mean, but because we don't have it, we compute the statistic of the samples, and then we hope that this one is as close as possible, to the true mean. So how can we make sure this is close to the true mean of this population? This is a question that as a data scientist we should answer, and there are a number of ways, and this is a very well studied field to do that. What I want to emphasize to understand when you are doing inference, what you are doing, right? So related to that is sufficient statistics. So let's go back to our example regarding the M1 and M2, which was the mean of number of times that each student check Instagram and Facebook, right? So if you provide a mean M1 and M2 as the statistic, that gives you the sufficient information from the population. Then that means everything is right. So you don't need to know any other information about these two populations. Let's say I give you another example. If I tell you the average grades for this class is 80 and average grade for another class is 30. So that gives you the entire information you need to know about this population, or there are some other statistics you need to know. So if I, for instance, if I have a probability distribution, which will later on more formally introduce that, but let's say if the distribution of the grades for a data science course looks like this, whose average is say 70, and also I give you another population whose average is 80. What do you think? So is it some two numbers will provide all information about these two populations? Definitely not. Why? Because if the second population distribution looks like this, so this is 80, then we definitely know if we call this one M1 and this one M2, M2 is greater than M1. But that doesn't mean that there's no students in M1 whose grade is greater than all students in class 2. So we usually expect that students in class 2, they have higher grades than students in class 1. But as you see, according to this example, there are some students in class 1 whose grade is greater than M2. So these grades are greater than M2. So as you see, we need to know also other statistic about this population. In here is standard deviation of grades. This is why when we post the grades, we post the mean and also median and also standard deviation. So by standard deviation, you know how the grades are spread and how the grades are close to mean. So therefore, we need to know the sufficient statistics about the population. That is particularly important later on in this course, because when we are talking about machine learning algorithms, when they come with some sort of uncertainty, then we are studying a population that which we don't have a clear picture about the distribution of that population. We want to know what is the sufficient statistics of this population. So formally, the sufficient statistic is sufficient if it can identify the probability distribution of that population. For instance, for our grades, usually our grades are following a normal distribution. As I said, we will talk about distributions in more details later on, but let's say the grades follow, that means the distribution follow a normal distribution. A normal distribution. So what you need to know about this, so if you know these grades are normally distributed, so what do we need to compute in order to have all information about this probability? Yes, we need to know the mean, and we need to know variance, or also standard deviation. So this is called sometimes mean, and I call sometimes variance. So if you know the mean and variance of this distribution, then we know everything about that. In other words, if you provide any other statistical measurement from this distribution, this is already contained by mean and variance. So the normal distribution is completely identified by these parameters. But not all populations are normally distributed. They have different type of distributions. We'll talk about this later. But whenever we talk about a sufficient statistic, this is the assumption. We have a population, and this population follows a probability distributions, hopefully a known probability distribution. And this probability distribution has some parameters by which This probability is completely identified, and these parameters are called sufficient statistics. These parameters called sufficient statistics. So now we are ready to talk about some distributions and more about the probabilities, and then some measurements of probabilities, and then we will get back to statistics and also statistical measurements, and then how, if you are given some data, how you can provide some statistical measurements about this data, which gives you some insight about this data, and then by which you can also compare your data with other data sets. So for next, I'm going to talk about some famous and popular distributions which we will use throughout this course. So before we talk about distributions and also some parameters and some other definitions, we start off by introducing random variables. So random variables is a variable that is subjected to randomness. So when we are not certain about a measurement, then we have a random variables. Or in other words, if we consider the probability distribution as some black box or machines, then the input to this probability distribution are random variables, and the output is a number between 0 and 1. Or another way to define a random variable is a variable that is drawn from a distribution. So if we consider a population, and if we assume this population follows a distribution, then if we select a sample from this distribution, that's a random variable. So if we denote that random variable by x, so then x, we are not certain about x. We only can say the probability that this x could be a number or an object or something else. There are two types of random variables: discrete random variables and also continuous random variables. And so a discrete random variable is a random variable which is drawn from a discrete distribution, and a continuous random variable is a random variable drawn from a continuous distribution. So what are the continuous and discrete distributions? The probability distribution, as I said, is a mathematical function that provides some probability of a certain random variable occurs. So that function is called probability distribution. Or if you wanted to look at in another way to a probability distribution, you're all familiar with the histogram. Or so in histograms, we basically count the frequency of occurrence of samples, and then we can say this sample occurs this amount of time, or 10 times, 5 times, and then we normalize the histogram, we obtain a probability distribution. There are many different types of probability distributions in statistics, but here I briefly introduce two of them, one from the continuous group, another one from discrete groups, but there are maybe 20, 30 popular probability distributions, but in field of data science, we only focus on maybe 4 or 5 probabilities, namely the Gaussian distributions, multinomial distributions, Poisson distribution, Dirichlet distribution, and Cauchy distribution. So these are, and also exponential distributions. But about normal distribution, which sometimes you also call it Gaussian distribution after Gauss, who first come up with this form for this probability distribution. In some contexts, they also call this distribution a Bell distribution due to the shape of this distribution. As I said, a probability distribution can be considered as a type of like a histogram. If you look at this figure, so this figure we have a histogram where each bar represent the frequency of occurrence of a random variable. So let's say this is a random variable I. This random variable occurred this amount of time. However, because these counts might be different in different events, we normalize this count such that the area under this curve would be 1. Only under these circumstances, we can call this curve a probability distribution. So a probability distribution has two main properties. The first one is the probability distribution, if we consider a probability distribution as a machine where we input a random variable, and then we get the probability of x, P of x should be bounded between 0 and 1. So we cannot have a negative probability of probability more than 1. And the second property is if you compute the area under this curve, which represent the probability, this area from minus infinity to plus infinity, P of x, the x should be equal to 1. Right? That's the two properties of that makes a function to be a probability. Perhaps you can make your own probability distribution which define for some phenomenon we are dealing with. But usually we are using the popular probabilities. Perhaps the most famous probability or distribution is a normal distribution, because many of the phenomena, they just follow a normal distribution. So in here we have a function for probability distribution. Basically, y is P of x. So P of x is equal to y is the output, which y is greater than or equal to 0 and smaller or equal to 1. That's the probability. This is the form of the probability distribution. Normal distributions are a subcategory of exponential distributions. So these distributions are called exponential because there is an exponential term in here. So E in here is an exponential function. So I think you're all familiar with the exponential function. E to the power of x, E is an exponential function. And the power of these exponential function is the input minus mu divided by 2 sigma squared. So mu is mean in here. Mu is a Greek letter, and also sigma is another Greek letter which usually used to represent the variance. So this is the variance. Well, we know that the square root of variance is a standard deviation, and here we have pi, which is the famous number pi, and in this sigma in here is the standard deviation. That's a form of a probability distribution, but most important thing, you should always be careful. We only consider in here a one-dimensional Gaussian distribution, but in data science problems, we are dealing with multi-dimensional normal distribution or multivariate normal distribution, or also multi-dimensional normal distributions. We barely work with one-dimensional data. So that's the normal distribution. Later, I will also give you the formula for multi-dimensional case. Another very basic distribution is Bernoulli distribution. Basically, this is a very famous distribution for when you're conducting an experiments. There are only two cases, basically success or failure. And then for each of these event, we assign a probability. So basically, we have P is probability of success, and Q, which is 1 minus P, because the space of this probability has only two outcomes, failure or success. And this is a discrete distribution. So normal distributions are continuous distribution because the random variable is continuous. But the Bernoulli distribution is a discrete distribution because the input or random variable is a discrete random variable. So as you see, here is the probability distribution for Bernoulli distribution. We usually use this notation for Bernoulli distribution. So X follow a Bernoulli distribution. So as I said, I also forgot to tell you about the sufficient statistics. So for Gaussian distribution, the sufficient statistics are mean and variance or standard deviation. So that means if I have the mean and if I have also the standard deviation, then this distribution is completely identified and I can compute the probability for any random variable drawn from this distribution. So you don't need to have any other parameters. So this is a function, this is a machine whose parameters are mean and standard deviation. For the Bernoulli distribution, the sufficient statistics is only P, the probability of success, because the probability of failure is 1 minus P. So then this distribution is completely identified by P. So this is why we call it X is a random variable whose distribution follow a Bernoulli distribution with parameters P. Or we can also say it in another word, X is a random process whose distribution is governed by Bernoulli distribution. So this is the different terms we use. And as you see, this is the probability distribution for Bernoulli distribution. As you see, we said the area under curve of probability distribution should sum up to 1. So what is the area for these? So this probability distribution is a discrete, only has 2 samples. So we only need to compute the probability that X is equal to P plus the probability of X equal to Y minus P, which is equal to 1. In other words, the sum of these two numbers will add up to 1. So that has all property of a distribution. The reason Bernoulli distribution is a very simple distribution, but we build up the multinomial distribution from the Bernoulli distribution. So I won't talk in here about multinomial distribution because well, we don't consider too many distributions in this course. We mainly focus on Gaussian distributions. But I will give you some reading materials for those of you who are interested. I would highly recommend to also read the multinomial distribution and also Dirichlet distribution, because these distributions are very frequently used as the prior distribution for hyperparameters in machine learning problems. So here there is some famous normal distributions. We have normal distribution, uniform distribution. Also, I wanted to take a moment and talk about the uniform distribution. So uniform distribution is that the probability of any random variable is drawn from this distribution is a fixed number. So there's a similar chance if you draw a number. So basically, if you have a probability, a uniform probability distribution from random variable A to B, so if this is P of X, this probability distribution basically completely identified by 1 over B minus A. So the probability of each of the samples drawn from this distribution is 1 over B minus A. And then if you compute the area under this probability distribution is equal to 1. Also, we have some other distribution like F distribution, chi-square distribution, exponential distribution. Also, note that for the exponential and chi-square and F distribution, they have the probability that these are positive distribution. They are not defined for negative values. So if you have some data whose probability follow only positive numbers, you can use the exponential distribution. For instance, for in genomic applications, the gene expression profiles before we taking the log, they follow exponential distribution if you plot them. So how we figure out that these random processes follow a distribution? One way is if you have enough sample, we basically plot the histogram, and then when you have the histogram of that random processes to see to which distribution this histogram looks like, and then we can identify the parameters. But as I said, unfortunately, we are not working with one-dimensional data. We are working with data of dimension thousands, millions. Therefore, this is very hard to visualize the probability distributions. They're also a very complicated sort of probability distribution. These are called Gaussian mixture models, a mixture of some Gaussians that can model very complicated distributions. I will talk about them when we talk about unsupervised learning. Okay, so far we defined the random variables and also sufficient statistic, probability distribution, and then we have some important statistics that we can compute from our samples. So the idea was like this: we have collected some samples from this population, and then we wanted to compute the sufficient statistics, and hopefully these sufficient statistics these statistics are sufficient or completely identify the true distribution. Perhaps the famous statistic computed from our sample is called expected value or population mean. So for now, when you wanted to compute an average of some numbers, what we do, we basically sum them up and then we divide by the number of samples. So this is the formula we have used for this the sample mean. So this formula, which is mu, usually we use for the mean, is called expected value of x. So this is e just an acronym for expected, and x is our random variable. How to compute that one? Imagine that x is drawn from a discrete probability. So, and then we multiply each random variable by the probability of occurring that sample. And then we sum them up for all samples. So assume that we have R samples from this population. If you wanted to compute the expected value, we multiply that sample by the probability of occurring that sample, and then we sum them up for all samples. This is very similar for what we previously doing. So imagining that we have this sample space, which I represent by a vector 1, 1, 2, 2, 1, 3, 4, right? And then also 3. So if I ask you to compute the sample mean for this data collected from a population, simply the way we compute the sample mean is we adding up these numbers, 1 plus 1 plus 2 plus 2 plus 1 plus 3 plus 4 plus 3, right? And then we divide by the number of samples drawn from distribution. 1, 2, 3, 4, 5, 6, 7, 8. We divide by 8. But I can write down this formula in another way. So I can say x is equal to 1 over 8. Then in here, I have, how many ones I have? I have 3 times 1 plus, how many 2's I have? I have 2 times 2. How many 3? I have also 2, 3, and I have 1, 4, plus 1 times 4, right? So this is how we compute the mean. So if I applied 8 to each of these terms, then x bar is equal 3 over 8 times 1 plus 2 divided by 8 times 2 plus 2 divided by 8 times 3 plus 1 divided by 8 times 4. So what does it mean? That means if you want to compute the mean, what we do in here, we basically compute the frequency of each event or random variable, and then we sum them up. So in here, the chance that we get 1 is 3 over 8. It's 3 over 8. So it should be 8. The chance that we draw the 2 from this distribution is 2 over 8. And the chance 3 is 2 over 8, and 4 is 1 over 8. This is exactly how we compute the expected value. So I can write down mu, which is expected value of x, is equal to the sum from I equal to 1. How many samples do I have? 8. So let me write it in here because so mu, which is expected value of x, which is the average or mean, is equal to sum from all samples drawn from distribution. We have 8 samples, xi, probability of x equal to xi. This is exactly how we compute. So the probability, so x1 is 1 times the probability of x1 is 3 over 8 plus 2, the other sample, the probability of the random variable is equal to this 2 over 8 plus 3, the probability of this random variable is equal to 3 is 2 over 8 plus 4, the probability is 1 over 8. So that's exactly how we compute the expectation value. So one problem is we need to know the distribution of samples. So for instance, if the samples are drawn from a normal distribution, we have to compute this probability for all these, for each of these random variables drawn from this distribution. So this is expected value or average or mean. So for some distributions, we need to multiply by their own probabilities, not simply sum the number up and divide by the number of samples. Another important statistic is variance and also or standard deviation. So variance is computed very similar to expected value, but instead of multiplying, so we have a random variable, instead of multiplying that random variable to the probability, we first subtract the mean from that random variable, square it, and then multiply it by probability that random variable occurs. And then that we sum them up for all samples. So for instance, for our previous case, R in here is 8, so we have 8 samples. We already calculated the mean, so we extract each sample from mean, square, and then multiply by numbers. So it can be also simplified, just multiplying the square of each sample to the probability distribution, and then subtract the square of mean. So these two are equal. So for a population whose distribution is normal or Gaussian, we can apply these two formulas to compute the probability, to compute the sufficient statistic. All we need to know and be able to calculate is probability of occurring a sample. So we also can express this sum in terms of a vector operation. So I can write it down. The variance is the expected value of, if I use a vector, so vector x, which are sample, minus mu is the average times the vector 1. This is transpose of x minus mu vector 1. We already talked about this vector 1. I put this arrow to make sure that this is a vector, so this is 1. Okay, so then taking the expected value, we can have this vectorized form, which highly recommended, and I suppose that all of you, when you want to implement data science, machine learning algorithm, you use the vectorized form. Anyway, so two sufficient statistics are mean or expected value and the variance. Next topic is joint probability. As I said, in this course and in data science, we are dealing with high-dimensional data. And for high-dimensional data, we don't have only one-dimensional distribution. We have multi-dimensional distribution or multivariate distribution. For those purposes, we define the joint probability distribution. So if you go back to the initial example for when I introduced the basic of probability, if you recall, we were supposed to compute the average number of times each student checked the Facebook and also the Instagram. So if you put these two values together, then we can have a vector. So it has x1 and x2. Okay, x1 basically in here represent the number of times this particular students check the Facebook, and X2 represent X number of times this particular student check the Instagram, right? So then we say X is a random vector which has two random variables. So what is the probability of X, or what is the probability of X1 and X2? This is a joint probability of these two variables. So I can have now the joint probability in here, Px1 and X2. So what does it mean? That means if I wanted to say compute the probability that X1 is equal to, let's say, 500 and X2 is equal to 100, that means the probability that for this student drawn from the sample of Stony Brook students, the probability that this student checked the Facebook, and here for Instagram, if the probability that this person checked the Facebook 500 times and the probability that this person checked the Instagram 100 times, what is this probability? So this is a joint probability with two random variables. In practice, we can have a joint probability of n random variables. Each random variable represents one attribute of this population. For instance, you can consider the population of, again, Stony Brook University students, and also we consider the weight. So let's say we have three attributes: weight, height, and average GPA. So each of these attributes is a random variable, and if you want to have a probability, a distribution probability of, for one particular student, let's say, whose weight is 150 pounds and whose height is, let's say, 6 feet, and whose GPA is, let's say, A, that means we are dealing with the joint probability. We are not only interested to compute probability for one random variable. You wanted to compute the joint probabilities for all random variables. So this is a joint probability, which we'll use frequently when we talk about inference in statistical model. So when we present a vector, I want to compute the probability of vector. That means the probability of each element take a certain values, right? Okay, so when we deal with the multivariate distributions or joint probability distributions, we have a number of random variables. So in particular, when you're working with high-dimensional data, computing these probabilities is extremely difficult and also computationally expensive. Ideally, what you wanted to have, each of these random variables, you want it to be independent, so from each other. So that means if you're collecting some attributes for a prediction problem, for an inference problem, what we wanted to have is attributes or features that are as independent as possible. If this is the case, then the joint distribution of random variables can be factorized to individual probability distribution of random variables. Let's take a look at the case when you have two random variables. The joint probability distribution is probability of x1 and x2. So for instance, again, you can also consider x1 is number of times a student check Facebook, and x2 is number of times that student checks the Instagram. If these two
random variables are independent, then instead of computing the joint probability, we can compute the individual probabilities and then multiply them by each other. And then if you have n random variables, the probability distribution, joint probability distribution is factorized to the product of the individual probabilities. So that's very straightforward, but the problem is in many cases and many applications, we really don't know if the random variables are independent. And actually investigating if random variables are independent from each other is a separate topic involving in statistics and linear algebra, that we basically verify different techniques to see if the random variables are independent or not. There is no straightforward way to show that if they're independent or not. But have in mind, in almost 90% of cases in data science, we wanted to have independent feature space. Then another note is on marginalization of a joint probability. So usually we obtain the joint distribution or joint probability that governing n random variables, but at the end we are interested to compute the probability distribution for one random variables. For instance, let's say if you have a joint probability distribution of x1 and x2 is given, but you wanted to compute the probability distribution of x1. So how to compute that one? This process is called marginalization, that computing the probability distribution for a one or a subset of random variables in a joint probability in order that calls marginalization. So marginalization is done as follows. We basically we keep the random variables, we wanted to have the probability distribution intact, and then we compute the probability distribution for all the values of the other random variables. So let's say our x1 can take these values. Let's say 1, 2, and 3. And also x2 space is A and B. So that means the sample space for x2 has two observations or two samples, and for x1 is 3 samples, 1, 2, and 3. And then we know that the random variables is just not, they could be anything, it's not necessarily a number. Then if I wanted to compute the probability that x1 is 2 and x2 is, if I wanted to compute the probability x1 is 2, then I need to marginalize over x2. So x1 is 2, and x2 can get all values from its sample space. So x basically, if I put it here, xi means xi belongs to all sample space of x2. So that means this is equal to probability that x1 is equal to 2, x2 equal to A, plus the probability that x1 is equal to 2 and x2 equal to B. This is called marginalization over a random variables. So the output of this is equal to Px1 equal to. This is called marginalization. And then we actually did this process a lot in order to do inference. For instance, let's assume the x2 is our input to the model, and the x2 is output. And then you wanted to compute the probability that for output when you have the joint distribution. So you need to marginalize over the input, right? That's one example. Another way in Bayesian inference, we extremely, this marginalization is important because sometimes we also want to do reverse. We have the probability distribution for one variable, but we wanted to express this as a joint probability distribution. So this is very popular trick. So let's say if I have px1, how can I express px1 in terms of the joint probability? So I would say, okay, this is equal to marginalizing over x2, px1, and x2. That is called marginalizing. Now in here I have joint probability, and I can do further processing with the joint probability if the calculation is easy to have the joint probability. So marginalization has many applications in stats and inference, in probabilistic graphical models as well. So the take-home message is to understand what is the concept of marginalization for joint distributions. Next type of distribution is cumulative distribution functions. So I just show what is a cumulative distribution, or also sometimes for the sake of simplicity we call it CDF. The CDF, the cumulative distribution function, is the cumulative distribution for, if let's say if I wanted to compute the probability distribution for x1 to xn, is probability distribution that the random variable x1 is smaller than 1 and all the way to random variable xn is smaller than xn. But let me give you a simpler example. Let's the instructor an instructor has released the student's grade, right? And then he says that 10% of students fail, get F, and also 20% of students get between C and B, D and B minus, and then 60% of students get the grade from, let's say, call this one B minus, and then get from B from B to A minus, A minus, and then 10% of students, they get A. So if I ask you what is the probability that the grades for the students in class, the grade is smaller or equal than B minus, right? So it's very simple. If you wanted to do this, basically this is equal to 20 plus 10, which is equal to 30%. With 30% in terms of probability, this probability of grade smaller than B minus is 0.3. So this is basically 0.3 is cumulative distribution of F equals to B minus. So if I ask you to find the cumulative distribution function of grade is equal to B minus, that basically, I don't know why I'm using this minus in here, is equal to 0.3. This is a cumulative distribution function. Another way, if we wanted to show it using the probability distribution, like a shape of probability distribution, let's say this is a probability distribution, Gaussian probability distribution. Here is a mean, and this is x. So CDF for x in here is the area under curve for where the probability is smaller than x. So that's the probability, that's the CDF. So basically this is the cumulative distribution function for x equal 0.3. So that's how we compute the cumulative distribution. Next, we talk about conditional probability. I find out that many students, they have problem with conditional probabilities, and they're having difficulty to understand and also to simplify a probability when they're dealing with a conditional probability. So first of all, what you need to know, a conditional probability is a probability. It has all properties of a probability, right? So the conditional probability is probability for a random variable provided that or given that another random variable already occurred, or another random variable is now a deterministic values. So for our example in this class, if I ask you what is the probability that students check its Facebook 100 times, given that he checks his Instagram 10 times, right? So what will happen when we are computing the conditional probability? That actually conditional probability gives us a better way of computing probability when we condition on something already occurred, right? Already occurred. So for instance, again, if I say P of x1, probability that students check Facebook 10 times, given that I know that the probability that he checks Instagram is 1,000 times, because you know this, that this is a deterministic, now x is given, then you can compute x2. So basically, we can have two, so if I say this probability is equal to 0.10, 0.1, that means this student also, because he checks Instagram, he's so much addicted to social media, he also checks Facebook a lot, right? So if you wanted to express the conditional probability in terms of the joint probability, then that's the formula. So probability of x1 given x2. So if you want to be more specific about this probability, we should express it like this. Probability of x1 given x2 equals to a value, let's say x naught. That means now we know x2 is deterministic. It's not a random variables anymore. But anyway, we don't mention that one. So probability that, we read it like this. Probability that probability of x1 given x2 is equal to the joint probability of px1 and x2 divided by the probability of x2 divided by probability of x2. So what basically this formula imply, if if you wanted to compute probability for random variable x1, given the fact that you know what is the value for x2, this is equal to joint probability, the joint probability of x1 and x2, with condition that you normalize that probability with the probability of x10 already occurs, right? So that's the why we normalize that. And also, in many applications, as I said, we only have access to joint probability. So if you wanted to express this formula all about joint probability, so if you look at many textbooks, so it is conditional probability is expressed at px1 and x2 divided by, I only have the joint probability. So what should I do to get the x1? We just talk about marginalization. So I marginalize this probability over x1. Now the output of this joint probability x2. So what I have, I only have the joint probability on the top and bottom of this fraction. However, on the denominator, I marginalize the joint probability. So conditional probabilities are extremely important in field of data science because why? Because we wanted to do inference. When we want to do inference, when we wanted to do classification, then we wanted to compute the probability of some event given that something given, right? So because when we want to do classification, assume that you are given some images. Now we wanted to predict this is the image of a cat or dog. So we wanted to compute the probability that this image is cat given that we have access to those images. Or another example is probability that a transcript from a voice is A given that we have the voice in the speech recognition. So this is the basic for classification, pattern recognition, and inference in data science. So we use the conditional probability. It's inevitable if you want to get skill and mastery in data science without understanding fully what is the conditional probability. Another important application of conditional probability is in Bayes' rule. So Bayes' rule basically is a foundation and a pillar for a vast majority of inferences and parameter estimation techniques in statistics and data science. In fact, there are two schools of thoughts in statistics and also in data science, statistical data science. One of them is called Bayesians and another one is called frequentist. So Bayesian people, they use Bayes rules for doing inference. So let's take a look at Bayes rule. So what is Bayes rule? Bayes rule basically, let's say we wanted to compute a probability. This is a probability. This is a conditional probability. And this conditional probability is probability of H given E. So what is H? H in here is called the hypothesis. Probability of a target or a hypothesis given that we have some evidence. So this is called the posterior probability of H given the evidence. So H is evidence. For instance, for our example, E is evidence that we know this student check Instagram 100 times, 200 times. That's evidence. This is equal to P of H times P of H times P of E given H divided by P of E. So what is P of H is called prior probability. A prior probability that we know that what is this hypothesis. And P of E given H is called likelihood, And then this is a P of E is probability that the evidence itself is true. So this is E is evidence, probability of evidence. H is hypothesis. We want to make a hypothesis. So why Bayes' rule is so important? Because that makes the inference problem much, much easier. And also in another perspective, so Bayes' rule says if you have some observation regarding a phenomenon and you wanted to do inference, so this is called likelihood. We have some likelihood. You can multiply this likelihood by some prior knowledge and then do the inference. A very famous example is in the field of if we wanted to see if someone has a cancer or not based on the tumors sample we collected during the surgery. So these tumors which are selected from body they're all evidences we collected from this person. Now hypothesis is if this person has cancer. So based on this analysis we have done on these tumors, and then hypothesis cancer, no cancer. But if this is called likelihood, probability of H given, probability of E given H, probability of this is a tumor given that this person has cancer or not. So this is a likelihood. So we can, if you multiply this likelihood by some prior knowledge of this hypothesis, then we have a better, more accurate estimation. What is prior probability? Prior probability basically says the chance that a person has cancer. So it's very low. So sometimes, let's say for this example, you calculated the likelihood to be H given probability of evidence given hypothesis is 0.9. So you can, if you don't use Bayes' rule, you can say, 90% there is a chance that this person has cancer based on this biopsy we have done from the tumors, from these tumors we excise from the body. So this is very high likely that person has the cancer. But if the probability, if we multiply this one, let's say P of H, the hypothesis that a person is general with these characteristics has cancer is 0.1, then if you multiply these two, the probability of H given E is proportional to 0.9 times 0.1, which is 0.09. So that's a probability now dropped to 9% rather than 90% because of this prior. So this is why what we are doing, we are wanting to do inference. We wanted to find the probability of hypothesis based on inference. We do reverse. We first assume the hypothesis is this, what is the probability of evidence, and then multiply by the probability of hypothesis. This is called Bayes' rule. Bayes' rule is used in many inferences problems, and as I said, there is one main approach in order to do a statistical inference in data science. So please spend more time on Bayes' rule and then try to understand it. I will later on also upload more examples to read to understand what is the Bayes' rule. In here, I have adapted an example from the source given in here. You can read this one to see one of the application of Bayes' rule for some medical purposes, and this is a very famous example. And also you can refer to this link that has a very clear and in detail explanation about the Bayes' rule. Okay, so far we talked about the joint probability. And joint probability is probability of occurring simultaneously some random variables. So this is also called multivariate distribution. So distribution of, let's say in another way, what is this probability distribution of a vector? So we talk about the multidimensional array, and then we said we are expressing a sample with dimension n using a vector. So you remember that we said if this is x is a vector from, say, the real number with dimension n, that means x is a vector or a one-dimensional array of x1, whose value is x2, and xn is the last value. So if this is our vector, what is the probability distribution of a vector? What is the probability distribution of vector? And in fact, as I said, in maybe 95% of statistical inference we do in data science problem and also machine learning algorithms, we compute the probability distribution of a vector rather than a scalar. So then we should be able to find a joint probability, or also we call it a multivariate probability distribution. We only focus in here on multivariate normal distribution. That means each individual random variable in here follow a normal distribution, So this is the general format for a joint probability or probability of an array. So in here, it could be also be fx is probability distribution of vector x. So, okay, so this probability distribution, now you're familiar from the linear algebra with the matrix multiplication and operations on matrices and vectors, so it should be very easy to follow what is this probability. First of all, when we talk about multivariate normal distribution or multivariate probability distribution, not only normals, any other distribution, so we also use this abbreviation of multivariate normal distribution, or sometimes we call multivariate MVN, that's called multivariate normal distribution. These are some abbreviations used for multivariate or multidimensional distribution. So if you have presenting a vector to compute the probability distribution, and this is the probability distribution for vectors, the output is a scalar. It's only one number, a probability. So the here is a scalar, a number. So if that means, let's say x is a vector of the whose value are 10, 10.1, and 0, the probability of x then is, let's say, 0.8. We don't have something like this. Probability of x is a three-dimensional array, 0.8, say 0.1, and let's say 0.5 for each value. This is wrong. So probability distribution of vector output is a scalar. So what is this formula? This is as I said, a vectorized form of the multidimensional Gaussian distribution, where mu in here is mean, sigma is the covariance matrix. It is basically, sigma is a matrix rather than a scalar when we have the standard deviation. So this is a covariance matrix for something similar to standard deviation or variance for one-dimensional data. And then this notation you also are familiar, because sigma is, let's say, is an n by n matrix. This is a covariance. This is called covariance matrix. Covariance matrix. We said it come a cov matrix. So this one is determinant of the matrix. Right? You know, you're familiar with this notation in when we are dealing with matrices, these two bars shows this is a determinant of that matrix. So you can verify the output for this probability is a scalar. You can convince yourself because we have a lots of example. You implemented and verified the vector and matrix multiplication. The output of this process is scalar. So I will just show you in here. So x is an n times 1 vector. It's a column vector. U also is same, n times 1. And then sigma is n by n. And you can see if you multiply these, this one dimension after getting the transpose is 1 times n, and then you multiply by this matrix, which is n times n, and then this is a vector of dimension n times 1. So what is the output? The output is 1 times 1. So the output is a scalar. And then on the bottom is the determinant. Determinant is also a scalar. Scalar and 2 pi and k also, there are numbers. So the output is a scalar, a probability. So not when you're, I have had problem with this when you're presenting these to students and then ask them to compute the probability, then they're expecting to get something out as a vector, but the output is a probability and probability is a scalar. So pay particular attention when you are computing the multivariate normal distribution. For now, we only focus on multidimensional or multi-array normal distribution whose form is given in here. And exp also is exponential function. Sometimes we use only e. So if you want to, so this is a visual representation of a two-dimensional normal distribution. Two-dimensional normal distribution. So as you see, both in x and y direction, the data are distributed normally. And then when you have 3D, it's like a cone shape for two-dimensional normal distribution, whose mean is, let's say, here. Then I can get the mean. Mean in here is a vector, so if I get just mean is here, say here, this is, let's say, M1 and M2. We can also compute the variance and covariance. I will talk about the covariance matrix because we will use that one a lot in data science problem, and I want you all have a good understanding at covariance matrix, at this matrix. But for now, I don't want to confuse you, but when we talk about the correlation, we will talk more about the covariance matrix. So for now, just know that we have multidimensional distribution, that these multidimensional distributions, you can consider them as a function whose input is a vector from multidimensional space and the output is a probability. We only focus on normal distribution, and for normal distribution, we need to have the sufficient statistic. The sufficient statistics are mean and covariance matrix, and then mean is a vector and covariance is a matrix. So if you wanted to see how to sample from a multivariate normal distribution. Let's say I give you, we have a distribution, a two-dimensional, a 2D distribution. Let's say our example of Instagram and Facebook, the mean vector is 145 and 5.5. Note that in here, mean is not a scalar, mean is two-dimensional. For each attribute, for each feature, we have one mean. So this is two-dimensional. And then covariance matrix is given as 1, 0, 0, 1. This is one particular covariance matrix. That means the features are independent. We'll talk about this. If I say, okay, if you have this distribution with this sufficient statistic, now generate, say, what is the probability of x equal to 200 and x1 and x2 is 0.7. This is basically x1, x2. Compute this probability for these two-dimensional normal distribution. You can, from SciPy library, we can go through these stat modules and then import a multivariate normal, and then by which we can compute the probability. So this basically normal distribution is P of x, and then what are the parameters is mu, which is the mean vector. Sometimes, as I said, we use mu for mean, and also the other parameter is the covariance matrix. So if you wanted to see how if you wanted to find the probability distribution for a multivariate normal distribution when you have the mean and covariance, then you can just get this function and compute it. Note that this is similar to 3-dimensional, 4, 5, 6-dimensional, n-dimensional data. If they follow a multivariate normal distribution, you can easily compute the probability using this function. So I think that's enough for this video. I will talk about some other topics in probability, namely I'll talk about correlation, which is a very powerful tools in order to find if data are similar to each other, and then how also we can use the Python libraries to compute the mean and also visualize that. That would be another video lectures, and then we can wrap up the basic of probability and stats for data science for this course, and then go to the topic of data wrangling, which means if you have some messy unstructured data, how we are going to organize them, and then how we're going to clean them and remove the noise and present them to our algorithms. So I wish you all a very good day or night, and I'll see you in next video.